global distinguished professor at Quran. An ongoing visiting position. I'm not sure how to describe that. So it's a regular 6 weeks in every fall. So he's certainly one of the leading experts in numerical analysis of applied mathematics. I know him for his work on conformal mapping, and so I studied conformal mapping my whole career, and occasionally I actually wanted to compute some of them. And he had written some of the best programs on Schwarzkopf, and his students have continued that. That was the state of the art work. I invited him here today because I was teaching the Math 331 course on problem solving in MATLAB, and he's an expert in MATLAB. In fact, Nick very proudly proclaims that he was the first person to ever buy a copy of MATLAB. He bought the initial release. He has even a little plaque in his office to this effect. That when I got assigned this course, I sent him an email immediately asking, what should I do, or what's your advice? Could you come teach it for me? So he came to give a guest lecture today. And while he was here visiting, I thought, well, he might as well give a talk for the Colloquium afterward. So that's what he's going to do. Among his other honors, he's a fellow of the Royal Society. He's a past president of SIAM, and also author of the first paper ever in tech as well. So someone who's had a sort of an interesting position in the history of
Forrest Gump.
Yeah. Sort of like that. Anyway, questions on random functions, random ODEs, and Chebfun.
Okay, thank you. It's wonderful to be here. As Chris says, I'm a numerical person, so that's what I'm good at. The talk has a probabilistic flavor, and I'm not good at that. I am not a probabilist. I'm not a stochastic analyst, so go easy on me. I'm learning these things, and as you'll see, it's leading in interesting directions. I should say a word about this picture. So that's the Andrew Wiles building at Oxford. And there's a lot to be said about that. One is that Andrew Wiles' office is right there, which is kind of embarrassing for everybody, especially Andrew Wiles, because he wasn't on our faculty when the building was named. The Clay Institute gave the founding gift. But then later he came to Oxford, so it's very weird to have him in his own building.
We sort of know what that's like here.
Yeah, that's right. Another thing to be said about the building is originally it had a monolithic structure, but the city council rejected the architectural plans and said that there had to be a view through the middle. There's a nice tower in this direction. So this common room was put in, and that broke the symmetry. So suddenly we ended up with applied mathematics there and pure mathematics there. So my office is over there somewhere. And the third thing to say about the building, I only just learned last night, I guess. I didn't know the name of the tall building in New York, right? How many people know the name of the second tallest building in New York after the Freedom Tower? No, that's like Fifth or something. So it's the pencil-shaped one.
Is that Billionaire Warehouse on Park Avenue?
Yes, that's not what it's officially called. So it's called 432 Park Avenue. Yeah. But it turns out it's the same architectural company, Raphael Vignoli, and it even has a sort of a similar thing. If you look at it, you'll see the beige outlined square windows. So who knows? Yeah. Okay, so that's me. So the way the talk works is there's PowerPoint, but it's also interleaved with demonstrations showing you what happened. Yes?
So, Andrew, when you have offices low down, is it more advantageous to have low down than fires or something?
Well, it's funny you ask that, because there was a fire drill not long ago, and we all wondered if we'd finally see Andrew Wiles. But no, he didn't appear. Not that I'm aware of, no. It tends to be different groups. This is numerical analysis. Biology is up here. You know how it goes. Okay, so we're talking about random things. So to set the stage, there's an icon for randomness. Let me say a word about randomness. This has been with mathematics forever, of course, and also science. But something's happened in the last 10 or 20 years, and it's just become much more important. And I see this from several angles. In mathematics, even in pure mathematics, somehow stochastic things are now central in a way they didn't used to be. And in engineering and computer science, it's just astonishing how the whole big data, machine learning, Bayesian, this and that, it's really changing in an astonishing way. So well, I did my PhD in the Stanford CS department, and probability was nowhere in this picture. Of course, I knew the odd faculty member or the statistics department, but this was not part of our education. And now every computer scientist is doing probabilistic things in part. It's an amazing change. The icon reminds us all that randomness has this jagged feel about it. Now, I've spent the last 15 years with my research organized around a project called Chebfun. That's the name of the software. The intellectual project is to study algorithms that are continuous analogs of familiar discrete things. So in MATLAB, for example, if you have a vector that would contain numbers, we are overloading familiar MATLAB algorithms to new algorithms for the function analog of those vectors. So vectors become functions, matrices become operators. That's the frame I've been working in. The basis of it is smooth. The functions we deal with happily are smooth functions. That's when a Chebyshev series converges fast, or they're piecewise smooth. We're perfectly good at piecewise. You could take the absolute value of that curve and it wouldn't trouble us. But the top curve is precisely what we haven't been doing. And then last year, there was this postdoc who needed 6 months of funding. This was Abdul Haji Ali, and he was a stochastic guy, and the Chebfun project had the money to pay for him. So we faced a moral quandary, or challenge, how to do something worth doing in the framework we had developed so far, but touching the stochastic world. And in particular, because our thoughts are very much organized around software questions. There's a software question. In any computer language, you'll have a command for making a vector of random numbers. What's the useful continuous analog of that command? If MATLAB's going to overload this, if Chebfun's going to overload that command, what should the overloaded command do? So that's what the talk is about, and I'm going to talk a bit about 1D and then 2D and then move into random ordinary differential equations. Okay, so 1D first. So the question is, what's a random function in 1D in a way we can work with computationally? So it was clear to us we had to start with a definition that would give you smooth functions because that's what we can do. It's all computational here. We're not trying to reinvent the theory of random functions. We're trying to do something useful and interesting on the computer. Of course, whatever we do should be stationary, translation invariant. And the obvious starting point is that whatever a random function is, at each point it should be a sample from the standard normal distribution. So this means mean 0, variance 1. Clearly, our random functions should look like that at each point. So this is what we decided to do. It's not the only solution that meets those criteria, but it's a simple one. We decided to start from Fourier series with random coefficients, but finite Fourier series. So imagine a finite series. I've written it in real notation, cosines and sines and a constant term. There's a parameter m that tells you how long the series is. And because there are two m plus 1 terms in the series, we simply set each of them to a variance 1 over 2m plus 1. So 2m plus 1 terms, each has a random coefficient, independent sample from the standard, from a normal distribution with mean 0 and that variance. So that's the simplest thing we could think of to start from. But what is m? There's got to be a parameter here. So we decided, let's call it lambda for a wavelength. So we have a wavelength, kind of the minimum wavelength of our random function. That determines m. You can think of it as 1 over m. M is 1 over lambda. It's not actually 1. It's the length of the interval divided by lambda is the right thing to do. Because sometimes we want to work on an interval 0 to 2 pi, other times on intervals of other lengths. Of course, the shape of the function shouldn't depend on how long your interval is. So this is what we tried. Now, I had never even heard of a Gaussian process when this work began, but believe me, everyone in the machine learning community knows about Gaussian processes. These are hugely important, an old idea that is becoming better and better known and more widely used. And I'm not talking about this stuff the way the Gaussian process people do. They will specify a covariance function, and this is equivalent to doing that, but that's not my point of view. So there's a couple of pictures. In Chebfun, you work with functions. So for example, there's an example of what you might get if you construct the function randfun with parameter 0.2, and here randfun with parameter 0.05. You can see the wavelength shrinking down. The formula is periodic. That's Fourier series for you. A priori, there's no user reason to want a periodic function. That's just a mathematical route to an end. So we do what any engineer would do. We construct it on a larger interval and then chop. And of course, you could talk about the mathematics of that. Some people call that circulant embedding. Circulant matrices are periodic. Toeplitz matrices can be embedded in them. So, of course, anything you do in this territory has a lot of literature and a lot of knowledge out there. And it seems that a key paper was by Paley, Wiener, and Zygmunt in 1933. Now, that's 10 years after Wiener did his celebrated work on the Wiener process and so on. This, of course, Wiener is the big name in some of this early probabilistic work, but this by no means was his central approach to it. But those people and others were very much interested in random series. And the person I know who's done a great deal of that over the years is Jean-Pierre Cahan, who just died in May, I think, a French mathematician, with a beautiful book called Some Random Series of Functions, which would do infinite series like that and much, much more. The history is wonderful. It's totally fascinating how you had Weierstrass inventing functions that were non-differentiable everywhere. And those were deterministic. Functions with funny lacunary series, Fourier series, Taylor series, it hardly matters. But lacunary means a lot of gaps, but you could also take random coefficients. In some sense, it's the same kind of mechanisms, but it's a different tradition. It came later. But all of this stuff with random series connects historically and mathematically to Weierstrass and his non-differentiable functions way back when. Okay, so let me show the first demo. So I'll switch into MATLAB if I can. This tends to confuse projectors, so we'll see what happens. Do I do something? Yeah, it did it itself. Okay. So it's always fun if you demonstrate things. And the point is, Chebfun is an interactive system. It's made for computing, so let's do a little computing. Suppose I say F, I'll make that a little bigger, shall I? I'll say font 36. Okay. Suppose I say F equals rand n fun of 1. So I'm setting my wavelength parameter to be very large. And now I'm plotting that function. So there is an example of a random function. The default interval is -1 to 1. Now that's not periodic, but it's been constructed periodically and then truncated. Of course, the user might want a periodic random function, and our flag for that is trig. All of Chebfun is built on Chebyshev polynomials, but there's alternatives if you want periodicity built on Fourier series. So here you see, it looks kind of even. It's not even, but it is periodic. So these are functions you can do things with, because that's what Chebfun does. I could evaluate f at 0.2, or I could find its maximum or something. This is the kind of thing we do all the time. I could find its roots and so on. Let's make it a little more interesting. I'll shrink lambda to 0.1. So suppose I say rand n fun of 0.1. And here's an example I showed this morning in the class. Anything that is interesting about random functions is tempting, to play around. So there, for example, I'm going to plot two functions, f, but also its cumulative maximum. That's one of the things that Chebfun can compute. So you can see what it means, the cumulative maximum. It's obvious, the definition. There's plenty known about the cumulative maxima of random it's hard to finish that sentence and be precise. But anyway, a lot is known about this sort of thing. It grows at a rate. In fact, the book by Perez and who's the co-author of the Brownian motion book? That's right. That's a wonderful book for finding a collection of interesting facts. I think it grows at the rate log t with probability 1, basically. Yeah. And you can, I could compute like this, for example. There's another function. There's f squared. So these are just functions, but I've got them from a random process. And also, we're not restricted to smooth things. So, for example, there's the absolute value. This would be represented as piecewise polynomials inside Chebfun. I could even do, for example, let's suppose I plot the maximum of f and 1. So you can see anything you do like this raises questions that are hard to resist. How many peaks will there be? Yeah, no doubt everything is known about all sorts of things. Let me do one more thing before returning to the PowerPoint. Let's shrink lambda a little further. Suppose I make it 0.01. So now I've got something that is beginning to look less smooth. Of course, mathematically, it's still smooth. It's still a finite series, but it's beginning to look unsmooth. The variance at each point is 1, and the mean at each point is 1. So this particular sample should approximately have those properties. So if I say mean of f, I should get approximately 0. And if I say variance of f, I should get approximately 1. So there you are.
If you get some data that looks like that, will you deduce any reverse?
I don't. Yeah. I don't have anything to say on that subject. Of course, that's a very interesting question, given data, to figure out whether there's evidence that it didn't come from a normal distribution, that kind of thing. Very interesting. I agree. Okay, let's switch to 2D. So I'll go back to the PowerPoint. I think it's coming. It did last time, didn't it? Yeah, okay. So I've just shown you random functions in 1 dimension. Now let's do the analogous thing in 2 dimensions. So once again, we can write down some desiderata. It should be smooth. Yes? To ensure that what? Yeah. So it's a finite set of numbers, those coefficients, and these are just independent samples from the normal distribution. That's probability. You're adding up 2m plus 1. At each point, it's obvious. The non-obvious thing is how does one point correlate with a nearby point? So that's the issue of a covariance of a Gaussian process. But at each point, it's completely obvious, yes. That's what mathematicians do. They say it's obvious, and then they move on. So we're just adding up variances. Yeah, it's the sum of. I think it's obvious. Of course, if you think there's a genuine problem, let's talk about it later. But I don't think there is. In 2D, of course, we again are going to be doing something smooth. We again want stationarity, and now there's also a rotation issue, so of course we'd like isotropy, and again, of course, we'd like the standard normal at each point. So the analogous thing to do now, we're in 2 dimensions, so we have an x wave number and a y wave number, so the analogous thing to do would be to take a disk of Fourier coefficients. Each of these will have the same variance, so however many dots there are, you'll divide by that at each point. And the radius of the disk will scale inversely with the wavelength parameter. So exactly analogous to... Well, these are jitter issues, you mean. For any finite size, there's an issue, but as lambda goes to 0 and the radius goes to infinity, that issue goes away. Or is that what you mean?
It looks like it's organized according to the x and y horizontal and vertical.
Yes.
When you rotate, still the random
Well, I think the answer is if I take this and rotate a little, it will not be mathematically identical. No. However, as the radius gets bigger, that effect will go away. That's all. Yeah. And in the end, we're going to chop a bigger domain anyway, so it's not a big issue in practice. So that's what we do, and there's an example. We'll compute one in a moment. And these are also very well-known objects. They're called Gaussian random fields. So in 1D, you can speak of a Gaussian process. Here, you should call it the Gaussian field, but that word's been used for other things, so it's a Gaussian random field. On a sphere, it's fun to do analogous things. There, instead of Fourier series, you would use spherical harmonics with random coefficients. So there you have a random function on the sphere, defined in the very same way with a minimal wavelength, a maximal wave number. And incidentally, in both of these contexts, there's always the question of, are we interested in a disk or a circle? Our default is a disk, but some people are interested in circles. And you could think of that as a monochromatic alternative to these things. So suppose instead of a minimum wavelength, I'd like a fixed wavelength, but with a random orientation. Then you're in the business that the quantum chaos people enjoy, of random eigenfunctions of the Laplacian, that kind of thing. Absolutely.
So before you were showing the graph, what is this showing?
Oh, this is, I've colored the positives with dark and the negatives with, yeah. Thank you for asking. Here's a monochromatic picture. They are strikingly different, aren't they? But okay, so let me do the same here and play with that on the computer. So back to my MATLAB. So suppose I now say f equals rand n fun 2. Of lambda equals 0.1 and plot that. So now we have a two-dimensional function. There's some kind of surface plot. By the way, for people who like MATLAB, it always looks better if you type camera light. So now it's a much better picture. If you type it again, it actually puts on two lights. Every time you type it, there's more light. 3 is too many. That's just a function. So our point is always in this project is to try to bring a little closer together certain parts of mathematics and certain practical experimental capabilities. It's hard to resist playing with that. You know, what's the maximum value of that function, for example? Or there it is. You know, what's the integral over that region? So it's hard to resist all sorts of experiments. I don't like this way of plotting things. You could plot it in other ways. You could say contour of f, for example. Or you could say this, what we call these zebra plots. If I say plot f zebra, then you get the black-white thing. Axis equal is better. Except in England, they're called zebra plots. And let's just show a sphere while we're doing this. Oh, I wanted to show you something else. So I'll type something, and you have to figure out what it's going to look like before I type return. I'll say for h equals -4 in steps of 0.05 up to 4. Plot f plus h in zebra mode. What will that look like? Okay, hold on a sec. I haven't typed return yet. So this is a for loop. It's going to start -4, -3.95, -3.9 up to 4. So it's going to plot a whole succession of images, but they're shifted by different levels of h. Too many people talking, sorry.
But these will be like a zebra plot, but they're nested, so they'll start small and sort of grow.
Yes. So shall I do it? So it starts black, and then you see the pools are growing. So we keep shifting the level of the water. So what you can think of is you're pouring water into a random surface and seeing how it changes. And in fact, that's precisely the reason I did this, because I was talking with Ken Golden at the University of Utah, and he studies exactly this. He's concerned with ponds in the Arctic, and he claims that they have a fractal structure. And time is going in the wrong direction here. I should have gone from, let's see if we can do that. If I go from 4 to -4, does that work? Yeah, that's how I should have done it, because this is global warming. So the problem is that when snow melts, it absorbs much more. So as it gets darker, it absorbs more and more sunlight, and therefore more snow melts. And so he's concerned with modeling Arctic melt ponds in precisely this fashion. There's a beautiful phase transition. Of course, you can see at the critical 0 level, the correlation lengths are going to infinity and then finite again.
The picture should be independent of how you chose to set it up. Just the Gaussian aspect of the fact these 4D series or anything else. Would you say?
Well, certainly I would agree with that in some heuristic sense. I don't know what it means precisely. Heuristically, yes, of course. Yeah. The fact that we pick a particular series shouldn't matter very much. Yeah. Yeah. The variance of the distribution, but I just have a fixed function. So at each point it has a fixed value, and then I'm pouring more water in. I'm changing the level of H. Well, not really, because I've got a fixed random function from this distribution. And I'm just plotting one of those functions. Yeah, okay. But at each point it's variance 1, yeah. Do you see a problem?
If you just randomly choose the coefficient, that will not be the case.
That's the same question you asked before. If you're right, I need to know this. So if you think you're right, please don't go away after the talk. Tell me. Okay, can we talk later? Okay. Let me show you one more. So anyone of my age loves the artist Escher, whose engravings are very expensive. However, for very little money, we can make our own Escher. So let's do that. So I'm going to make a Chebfun corresponding in 2 dimensions, Chebfun 2, corresponding to the trivial function x on a rectangle. So this is the trivial function x on the rectangle from -2 to 2, 0 to 1. And now I'm going to plot x plus a rand fun with wavelength parameter that I happen to know will look nice. Same domain, -2, 2, 0, 1. Zebra mode. So there's Escher, right? Isn't it beautiful? You know, his metamorphosis shows the geese turning into whatever. You find when you explore random things that 2 things happen. One is they're visually sort of intriguing. You want to explore more, but also, questions just throw themselves at you. And here again, you see the correlation length. So obviously here the white dots are localized, and here the black dots are localized. But near the phase transition, fascinating things are happening. Okay, back to the PowerPoint, okay? We haven't done it in 3D yet, though, of course, not everything I've said would have analogs in any dimension. There's no zebra plot in 3D. Okay, so that was 2D. Now the second half hour is getting a little closer to things that are scientifically and mathematically more difficult. So what happens as the wavelength goes to 0, when things begin to look more like the noisy functions we're used to in stochastic analysis? So the first thing to say is these wiggly functions, as lambda goes to 0, don't converge, at least not as functions evaluated pointwise. They just get wiggling faster and faster. But because they're wiggling, their integrals do converge to 0. So here, for example, I have a rand n fun with a small lambda parameter. Its integral is not interesting. It's approximately 0, and as lambda goes to 0 with probability 1, that integral will go to 0. So that's not interesting. And the amplitude, it's just statistics, will decrease with probability 1 at the rate lambda to the 1/2. So to make it interesting, we rescale. So we take random functions and we divide them by that lambda to the 1/2. And so instead of what we call a smooth random function, it's now what we call a normalized smooth random function. And you can give Chebfun a parameter. So now we really do have a sum of Fourier modes with coefficients from the standard normal distribution, or a constant times that. So we're now really looking at larger and larger finite series where the coefficients all have variance 1, not 1 over m, 1. So that's pretty different. And the upper curve looks the same, except the axes have changed. The lower curve is also the same, but its axes have not changed, and therefore it looks different. So now you're getting something of size O of 1 in the integrals. So the indefinite integral of one of these normalized smooth random functions is what we call a smooth random walk. Of course, it looks like the kind of random walk or Brownian motion we're used to, and that's what it becomes in the limit as lambda goes to 0. Again, you can talk about the series underlying it, and now we really are close to Paley and Wiener and Zygmunt in 1933. So integrating the f that I showed you earlier, you get again a series with 3 terms in it, 3 types of terms. But thanks to the integration operator, you get a k to the minus 1. So imagine if this were an infinite series. It's an infinite series with coefficients decreasing inverse linearly. Of course, that alone is not enough to give convergence. However, these are random numbers, so the signs are oscillating. So with probability 1, it does converge. And this indeed is rigorously one way to describe Brownian paths that stochastic people know all about via random infinite series. So it really is true that as m goes to infinity, you really do get Brownian motion. And to make that a precise state, that can be made precise in ways that stochastics people are very good at. And I guess I need to show that on the computer too, because that's getting important now. So, so we'll go back to our 1D random functions, but now in this normalized mode. So I'll now say f equals rand fun of 0.01 normalized. So this will look just the way it did before, and only the vertical axis has changed. But the point is, when we integrate this, we'll get something of size 1. So now let's integrate it. And I'm going to do that like this. I'm going to set the seed of the random number generator, and then I'm going to plot the cumulative sum, which means the indefinite integral, of rand n fun of 0.1 in this normalized mode. So, oh, that's ugly. Sorry, I forgot this. The seed 0 gives you this very distracting effect. That's random. So one thing you learn about random functions is sometimes they don't look properly random. It's really annoying. So that doesn't look random, does it? So let's change it. Let's make it more random by changing the random number seed to 1. Good, that's better. This is random, right? So see what we've done. We've made a smooth random function, normalized it, and integrated. Cum sum in MATLAB is a cumulative sum of a vector. Of course, we're working with the continuous analog of that. And the point of setting the random number generator seed is I can set it again, but shrink lambda, and you'll start seeing more terms in the Fourier series. So suppose I say, hold on, and then I'll do the same thing, but I'll change 0.1 to 0.01. So because I've got the same seed in the random number series, I'm going to get the same function, but with more terms in the series. And you can see we're adding in some higher wave numbers. And you could keep going, of course, as long as you wanted. Here's 0.001. In the limit, it's becoming a true Brownian path. But each individual curve I'm showing is an entire function. It's always a finite trigonometric series. So I'm sure many of you have played with things like this. The flavor is completely standard, and yet what we're actually doing is not the standard way people do these things. The standard way that people deal with Brownian paths is pointwise. So you use your mathematical knowledge to evaluate the Brownian path exactly at this point and exactly at this point. And and then fill in more and more points if you wish. We're doing something different. We're approaching it via series, so there's no particular point at which the value remains the same from as you resolve more and more terms in the series. So a different approach to the very same standard limit. And just for fun, let's show you two more things. Suppose those of you who know Chebfun know that everything is vectorized, so we can do more than one function at a time. So for example, suppose I wanted to do 5 of these curves at once. I could say something like plot cumulative sum of rand n fun of 0.001 in normalized mode, and then I could say I want 5 of them. So what just happened is we constructed a Chebfun quasi-matrix with 5 columns. Each is a different sample from the same distribution, or let's try 50 of them. It's not especially fast because, well, it's not for all sorts of reasons. So you see, any stochastic person would be appalled at how slow this computation is. There's no need for it. In fact, I haven't done it before, and I never will again. But there you are. So there are 50 smooth Brownian paths. In 2D, I could say plot cum sum of rand n fun 0.001 normalized. But now let's make it the complex mode. So I'm thinking of it as a complex random function, integrating that. In other words, I'm in 2D. So that's a smooth Brownian path in 2D. And every time I make another one, that's another one. There you are. Let's do a couple on top of each other. Oh, I guess the color is always, I don't know. Oh, sorry. Yeah, okay. So now we're seeing different samples of Brownian paths, smooth Brownian paths in 2D. So going back to the PowerPoint, there are real issues here which are everywhere in stochastic analysis, and I want to say a word about that. Okay. So one phrase you occasionally hear is the white noise paradox. So white noise is a concept we all have. We all know the concept of white noise, but when you try to pin it down, it's a very difficult concept. Because, of course, it should correspond to the limit lambda going to 0, but the amplitudes are getting bigger. And when lambda is equal to 0, the amplitude is infinity with probability 1. The idea of sampling white noise, you cannot sample white noise at a point. There's no way I can give you a point value of white noise because it's with probability 1 going to be infinity or minus infinity. You can't do that. And yet somehow, of course, we want to talk about white noise. So there seem to be sort of two approaches. You can be a physicist or a Chebfun person and take the view that lambda is never really quite 0. Of course, in some sense, we want to understand what's happening as lambda approaches 0. But in any real problem, lambda is going to be positive. Then there's no difficulty. That's not the approach that mathematics has followed since Wiener. So essentially, mathematics has taken the view that we really want lambda to be equal to 0. We have to talk rigorously about Brownian paths defined with lambda equals 0. And why do we do this? Well, the advantage of this point of view, to my mind, is the overwhelming one that it's the right idealization for all sorts of conceptual reasons. So the analogy I love is just continuum mechanics. You think of the gas in this room. We experience it as a continuum. We have partial differential equations that describe it as a continuum, even though we know that, of course, there are 10 to the 32 molecules in the room bouncing around, which are the infrastructure. So reality is discrete in a sense, and yet we all understand that the continuous model is also reality in some intellectual sense. Nobody would ever argue that we don't want the gas law because gases are made of molecules. So that's the argument in favor of setting lambda equal to 0. There's no doubt that at a certain conceptual level, white noise really should be pointwise. The downside, as I'll be arguing in various ways in the next 15 minutes, is that that is a very technical thing to do, and it's hard, and to do it right requires a lot of expertise. Wiener was the first person to do it. Many people had preceded him in various aspects, but Wiener really connected rigorous probability theory with the idea of Brownian paths. And ever since then, more and more has been done in this direction. But let me remark on a few of the things that happen when you follow this standard route. So I've been telling you that noise wiggles and then you integrate it to get a Brownian path. That's not the way you do it when lambda equals 0, because noise is too problematic. You define the Brownian path rigorously, because that, at least with probability 1, is a continuous function, even though not differentiable. So Brownian paths become the primary objects in stochastic analysis. You can differentiate them if you're willing to talk about a distribution. So white noise does make sense as a distribution, but not as a function with point values. And of course, that's a fancy way of saying that white noise only makes sense when you integrate it. This all has the consequence that a new field is created called stochastic analysis. You don't take analysis and add a bit of randomness. You make a new field with new foundations. And there's an analogy here I won't go into that intrigues me. Einstein, I think I mentioned it in my abstract online here. Two of Einstein's famous things from 1905 had related mathematics in them. Both the blackbody radiation photoelectric effect work and the Brownian motion work both implicitly involve the problem of what do you do as lambda approaches 0. So let me say a little more about the history. So in the very olden days, you had the botanist Brown, who was one of those who observed Brownian motion. And probably you all know Brownian motion. You look with a microscope in a liquid that has particles suspended in it, and they're wiggling around. Why are they wiggling? Is it because they're alive? No. Digression. These two guys were not doing Brownian motion. They were founding statistical mechanics. So this is when randomness really went into physics. Then you had a remarkable collection of people in the beginning of the 20th century, remarkable for their mustaches as well as other properties. Everyone had good mustaches around 1910. It's a wonderful era. These guys were figuring out various aspects of stochastic behavior related in part to Brown, although Einstein hadn't even heard of Brown, it seems, until he was sort of writing up his work. He did the main work without knowing that this effect had been observed. Amazing. And then you had the extraordinary impact of Norbert Wiener, and so you can see he's a few years later. He was just a kid, a prodigy. He wasn't that old even in 1923, but he made it rigorous, and that was the starting point of the way most mathematicians view these things now. When you get into stochastic calculus, as we call it, and ODEs, the two standard ways of formulating that are Ito and Stratonovich calculus. And then the final thing I wanted to mention is just to emphasize how stochastic things have become center stage in mathematics. So here I've picked a Fields medalist from the last 3 rounds of Fields medalists. These are all stochastic people. That didn't used to be true. If you look at the early years of Fields medals, there wasn't a whole lot of stochastic stuff there. But now, mathematics has decided that stochastics really is at the center of the field. So Martin Heyer, for example, is an authority, the authority maybe, on stochastic PDEs. So my reading of the history is that, for whatever reason, the view among mathematicians, at least, is that lambda really is 0, by which we mean the only right way to talk about stochastics is with a pointwise concept of noise, even though there's no such thing as the value of white noise at a point. Other fields may behave differently. It seems that finance has followed this. Physics maybe less so. Biology, often yes. Those are 3 areas where stochastics are very big right now. Where does that bring me? Okay, I'm getting near the end, of course. Let's talk about differential equations. So ODEs are the easiest subject in all of mathematics. It's wonderful. Anyone who's a grown-up mathematician can practically figure out ODEs on the fly. It's just a beautiful, important, easy subject. Partial differential equations, not so easy. So you might imagine that we could take this easy subject and add a bit of randomness to it and we'd get something not so difficult. Well, that's not what has happened because the point of view that lambda should be 0 is so pervasive. So instead of ODEs plus randomness, we have a new field called stochastic DEs or SDEs, highly developed. I haven't written down the formulas, but it's built on these Ito and Stratonovich notions of calculus. So the very notion of integral has to be reinvented in the stochastic context to make this subject work. And if you've reinvented the notion of integral, of course you have to reinvent numerical methods. So in stochastic, in computing for SDEs, people don't use standard methods. That wouldn't make sense. You can't sample white noise at a point. So what would it mean to use a standard method? You have to reinvent the numerical methods, and so that's been done, of course. And two of the famous names are Euler-Majorana and Milstein. Oh, here's a digression. So one of the many nice books in this area is by Mikosh. And this is sort of typical about how a lot of books sort of start going in the stochastic SDE area. A lot of them are moving towards financial applications. Its theoretical basis is by no means trivial. Whoever tried to read the first few pages of a book on stochastic calculus will certainly agree. Tools from measure theory and functional analysis are usually required. In this book, I've tried to keep the mathematical level low. The reader will not be burdened with measure theory, but it cannot be avoided altogether. Of course, every book is different, but this point of view is a familiar one. Everyone accepts that stochastics is a technical area, and yet it's important, so somehow we'd like to talk about it. So we have a few apologies at the beginning of a book about how we're not going to do it properly. Of course, the physicist's alternative would be not to set lambda equal to 0, but keep lambda positive so that you never need to reinvent calculus. You only have to know what the meaning is of the things you compute as lambda gets smaller. And it's known that as lambda goes to 0, you get what's the Stratonovich version of stochastic calculus. The key papers on this seem to be by Wang and Zakai in 1965, though there's very little interest. In the mathematics literature, you won't find many people talking about smooth random functions, because somehow there's not enough challenge there mathematically, I think. Maybe a little more in the physics literature. There are a couple of interesting books about to appear. Claudin is the well-known name in numerical solution of SDEs, and he's got a new book coming out on random ODEs, but with no focus on the smooth case. There's also a book coming that I haven't seen yet by Zhang and Karniadakis. Karniadakis, he's Greek, obviously. I'm sure some of you know him. I know about this book from an email interchange. So he said, "I'd love to tell you more, Nick, but I'm on an island off the coast of Europe right now." Every Greek has an island, right? So I responded and I said, "Okay, I understand. I too am on an island off the coast of Europe." Then we've just finished a book called Exploring ODEs, which is just an ODE book, but Chebfun enabled and freely available. So if you're curious, please take a look at it. Chapter 12 of that book, there's the co-authors. Chapter 12 is about this random stuff. And we don't have any real publications because we haven't done anything mathematically new. It's a strange situation. I believe that from a pedagogical point of view, the stuff I'm telling you is potentially important. But there are no new theorems here. Everything in principle is known. I want to just draw your attention to one thing in the book, and we're going to finish in the last few minutes by solving some random ODEs to explore stochastic effects. So this is the way you can solve ODEs in Chebfun. We have a system called Chebop, a Chebyshev operator. You can specify your ODE with a hopefully obvious syntax. You give it an interval, boundary conditions, and then you type backslash to solve it. So Appendix B of the book is 100 examples where we do 100 problems and plot the results. Those are not stochastic, but now I want to finish by doing a couple of stochastic ones. The theme being that exploration is very easy when you're not held back by technicalities. So now instead of typing, I'm actually going to go to a M file that I've already got there. So I'll say edit. I think it's called random codes, or it might be an underscore there. No, there's an underscore. Good. Okay. So this is a collection of 6 or 7 little code segments. And if I run the first one, for example, that's not random. This is the area equation y double prime equals xy. I set it up with a Chebop and an operator and 2 boundary conditions, just to give you a sense that we're trying to do randomness exactly the way we do deterministic things. So if I want to solve an ODE, I do that, and out comes a picture. If I want to explore stochastic effects, I do the same thing, but some of the functions defined in my ODE are smooth random functions. So here, for example, y prime equals y plus a smooth random function. That's called additive noise. I think this will compute 6 trajectories and superimpose them. So there you see 6 samples. This equation diverges to plus or minus infinity, and which one it is determined randomly. So already there's some physics in there that people know a lot about, right? You can talk about all sorts of things. The next example is additive noise, but the sign has changed. So now I have a decaying ODE plus additive noise. And there you don't go to infinity, you stay near 0. So if I take 6 trajectories of that, you can see they're all oscillating around 0. The next one is what people in the business call multiplicative noise, where the random term is multiplying your term in the ODE. So here we're taking 6 samples of multiplicative noise. Now they're stretched out exponentially. In fact, the logs of these curves will be essentially the former curves. Experts know everything about these. All I'm doing is a very standard experiment in this non-standard smooth context. And now the final couple of examples are more interesting because they're nonlinear. You know, I don't know how many of you have studied this stuff, but in the normal treatment, you've just spent 3 weeks in a course learning how to discretize a linear ODE. What are you going to do for a nonlinear one? That may take further discussion if in the stochastic context. But here, we've decoupled that. We're just talking about ODEs, which we know how to solve by whatever black box, and we're giving them some smooth random coefficients. So here's a nonlinear equation that has steady states at 1 and -1. It's a bistable equation. We start at the unstable steady state of 0. That's our left boundary condition. But then there's noise in the equation. So let's see what happens. I think, is it 20? Yeah, 20 trajectories. So it starts at 0 and then, obviously, thanks to symmetry, with equal probability ends up going north or south. In this particular configuration, every trajectory will, with probability 1, keep crossing back and forth, but not very often. Let's bias the initial condition. I think it's 1.5, isn't it? So we'll rerun this experiment, but we'll take the left boundary condition to be 0.15. And you can imagine in an application, say a biological problem, it's very easy to see how this kind of experiment would be of application interest. So we'll bias the initial condition. How many trajectories go north? Well, almost all of them. Maybe it will be all for this experiment. Oh, no, not quite all. So, of course, there's lots of mathematics there that people know a great deal about. The final pair of blocks is for an equation where I've switched the sign again. So this one has a stable state at 0. But if you deviate from that stable state too much, then you go off to plus or minus infinity. So this is like tunneling in quantum mechanics. You have a metastable situation, and randomness is kicking you out of there on some time scale. So I'll run that. So that got kicked out very rapidly. That went off to infinity. That went off to infinity. So you see, in that experiment, a typical lifetime, the half-life of this radioactive nucleus was 30 or something, who knows what. But of course, if we change the parameters, things will change. So that was with an amplitude of the noise 0.25. Let's change the amplitude to 0.20. what will happen to the half-life? So we're running it again, and none of them escaped. And of course, everything's known about that too. So we're treading through very familiar territory in mathematics and physics, but doing it in an easier way from a, I think, pedagogical point of view, I hope. So let me summarize. Well, the standard in stochastic analysis is to conceive noise pointwise. An alternative is to take lambda bigger than 0. Smooth random ODEs are easy. They avoid the need for a special calculus. They avoid the need for special algorithms. They avoid the white noise paradox. There are lots of disclaimers. I've only listed a couple here. Nothing is really new. So if you're young, you can't do this kind of research because it isn't research. And this is the important one. I'm a numerical person. So if I show you a method, people are going to assume he thinks that's efficient. Well, I don't think this is efficient. This is not algorithmically competitive, but it's conceptually competitive. I think it's a good, clean, simple way for people to play with such problems. Multiple dimensions, I don't know much about. They probably have some further subtleties. I want to finish with an analogy. I talked about the air in the room. Is it really discrete? Is it continuous? Well, both are true. Continuous is kind of right conceptually. It brings complications. I think in stochastic analysis, it's the same deal. Lambda equals 0 is sort of right, but it brings complications, and it brings even worse complications. That's the kicker. So here's the analogy. What if we told students that they weren't allowed to talk about integrals until they'd mastered measure theory? That would be ridiculous. You can't set up a math department on that basis. But in some sense, I think that's sort of what has happened with stochastic analysis.
Because you can talk about it before you talk about it.
I spent the last hour talking about stochastics without talking about, I didn't define Ito or Stratonovich. That's my point. Yeah, I am the only, you will never find another person who spends an hour like this without defining Ito or Stratonovich. So I will finish with one final demo. Let's see. So let's see, how does this one go? I will say S equals, better do a hold off, right? S equals scribble. I'll say thank you, of course. But then we need to add randomness, right? So just to emphasize that everything is a function. So I've picked parameters that look nice, of course. And we want to be random in both directions, so I'll say complex. Axis equal. Oh, that didn't work, did it? Well, that's the worst ending to a talk I've ever seen. What did I do wrong? S equals scribble of thank you. Oh, I didn't plot it. That's what went wrong. Good, okay. Thank you very much.
Any questions?
Is there a use for other orthonormal bases? You mean besides Chebyshev? So everything I showed you was implemented at the lowest level with Chebyshev polynomials, but I never really mentioned that because it doesn't matter. Sure, you could use other bases. Nothing I said today would care very much.
You get randomness in the square by using your circle of coefficients and taking a double Fourier series. Suppose you wanted to get randomness on a disk, on a circle. And you wanted to use, of course you could truncate the square. Suppose you wanted to use...
Oh, directly, I see, yeah.
Fourier Chebyshev on a circle inside the circle.
Yeah, do you know the answer? I don't know the answer.
And partial answer.
Really? That's a fun question. I don't know. So afterwards, maybe if you tell me your partial answer, I'd love to know that. Yeah.
I was wondering, since Chebfun is based on Chebyshev polynomials, you were talking about Fourier series with random coefficients, but what about just using Chebyshev expansions with random coefficients?
So Chebyshev expansions are not translation invariant. They're wonderful for dealing with functions, but mathematically they don't have that crucial property. So I don't go near them from that point of view. You had a question?
Is there a particular reason you chose Chebyshev polynomials?
Well, so the great positive thing for numerical work about Chebyshev polynomials is very simple. They're equivalent to Fourier transform. And in particular, they inherit the wonderful property of the fast Fourier transform, which maps you back and forth between values and coefficients in n log n effort. So that's wonderful. If you expand in Legendre polynomials, it becomes a pain in the neck to go back and forth from values to coefficients.
So this method led to this, I can't say the name, Stratonovich version.
Yeah.
What is the difference between that and some other thing that would lead to the Ito version?
Oh, that's a good question. That's a great question. I don't know the answer. It shows how shallow my knowledge of this subject is. Ito has this, people say it's a martingale, but it has this way of being biased. It doesn't read the future in advance. Yes, but that's a great question. Would there be a way to do this sort of through my scenario? I don't know. I like that, yeah. My bias, based on little knowledge, is that Stratonovich is the more sensible thing to do, and what a shame it came along 15 years later. But not everyone shares that view, and the people who disagree know a lot more on the subject than I do.
Any other questions? I wanted to mention, I was planning to take the speaker to dinner tonight at the Country House around 6:30. If you're interested in going, why don't you talk to me afterwards, and we'll make sure there's a coordination of rides and so forth. Otherwise, thank you very much.